Okay, so let's get into some anchorage design. So there's two main classes of anchors: cast in place, which are placed before the concrete is cast, which is what this right photo is. They tend to be very high capacity, durable, very good option. And then post installed, where a hole's drilled and then the anchor is slid in, and either chemical adhesive, some kind of expansion, or even an undercut type head engages the concrete. Anyway, there's different dimensions given here on the studs, the headed studs, and then different strengths for different materials. Headed stud anchors are what we were just looking at. DBA is like a weldable rebar that you can shoot on to a plate with a stud gun. The studs are shot on. It's not like fillet welded. There's a gun that's specifically made to weld them directly to plates. Okay, adhesive anchors. You can see this cutaway view here where a hole has been drilled. The epoxy's put in. Usually it's an epoxy. And then the anchor's put in. It's good to test post-installed anchors. The code doesn't require it, but it's worth doing. It basically validates the installation. Here's some guidelines on the loads to use. So 200% of allowable, and then these ratios of ultimate and yield strength. Here's some examples of what I use for my projects, and you can see the forces get pretty substantial. From time to time, people complain about them and say it's not going to work, and then they test them and it works just fine. So it won't work if there's an installation problem, and that's the whole point of testing these. Okay, there's a photo from Simpson. Pretty cool. All right, so as far as designing anchors, there's 5 strength equations for tension and 3 for still, and they're a little on the burly side. Safety factors are here. You'll notice for post installed it gets pretty complex. For cast in place, not as much. One of the keys is whether or not there's supplementary reinforcing in the anchor failure surface or not. And you can see in this photo here there is some supplementary reinforcing. It doesn't look like it's much, so I don't know that I'd get too excited about that. But if it was heavier and the shear plane or the failure plane was going to intersect that reinforcing, the code allows us to go in and count that. Although I haven't put any of that into this PowerPoint. That would be for a second semester of concrete design. Okay, so moving on, the tension still equation. You basically take the cross-sectional area of the anchor times the ultimate strength and use that as the nominal strength, hit it with a phi factor, compare it to your loads. This table here gives you those values for different diameter of headed stud anchors, so that strength was given earlier. It also gives the pull-out strength, which is more a bearing of the head of the bolt on the concrete. You can see in general those are all larger for each anchor size than the still, which is great. And then the shear still, or the still value, but in shear, is given here. Okay, the next major failure mode, and this is usually what governs the design, is concrete breakout, and whether in tension or shear, usually the concrete breaks before the anchor will yield or the still portion will fail. So for a single anchor, this equation we use. For a group, we use this equation. All of these factors are just kind of a pain in the butt to find, but if you just kind of step through it one little bite at a time, you'll get there. So this ANCO is given by this equation, so 9 times the depth effective embedment depth squared. And then ANC is the actual failure surface. And usually why this is there is a lot of times the failure surface intersects a free edge before it would do a full cone. So in this figure, this would be a full failure cone for one anchor. And in here, you can see that it's multiple anchors, but what happens is the failure cone intersects a free edge. So we would base our ANC off of these types of figures. And the code has a lot more figures than this. Um, anyway, so the next pages just walk through what those psi factors are. And I would just say either look at these slides or jump into the code and read the sections and read the commentary, and that'll help enlighten you more as to why the factors are the way they are. So I won't delve into all of them. Third failure mode in tension is concrete pullout, where basically the concrete bears against the head of the stud and crushes and pulls out. Side face blowout. This is a problem where you have deep anchors close to an edge. Deep is defined by an effective embedment greater than 2.5 times the edge distance. And then the bond strength, and this only applies to adhesive anchors where you pull and the bond between the concrete and the adhesive can fail. Okay, so this table gives you kind of a feel for what types of values you can get for a 4-stud anchor plate problem with varying edge distances, so from 4 to 26 in one direction, and then different embedment depths right there. It turns out the anchor diameter doesn't really make much of a difference on these, so I think these were done for a 5/8 headed stud. It's really the compressive strength of the concrete that causes the variation. Okay, similarly for shear, there's a set of equations. For headed studs, for some reason, you don't have to hit it with the 0.6, which is usually what you do for shear. And then for other anchors, so it's 0.6 times area times the ultimate strength. Similar set of concrete breakout equations, but this time for shear. You can kind of walk through the psi factors here, and then this V sub B, it's the minimum of these two equations. Or if you have a stud plate, like a welded plate that the studs are welded to, this equation goes from 7 to an 8 factor on it. Okay, and then kind of the breakout area is similar to tension in concept, but functionally different. And the code has probably 3 or 4 pages of different configurations and what the equations are. So it's useful as you're getting into this to kind of play around with things. Then pry out is the last failure mode for concrete and shear. And that basically is this factor times the NCB or NCBG, which we saw earlier in the calc. So as you're doing the calcs for anchors, you'll calc NCB, and then when you get to pry out, it's just a simple factor on it to get to the capacity. Similar table for shear. So 2 different edge distances. Turns out the embedment height isn't all that critical for that. The pry out would play into that. All right, kind of the last 2 things. Sometimes, I shouldn't say sometimes, almost always we have combined tension and shear loading on anchors, just by the nature of the beast. So when we do that, we have a couple equations. We can follow this. If you look at this dark black line, you could follow that curve. So if your shear and your shear ratio and your axial ratio is inside of this, kind of like interaction diagrams for columns, then we're okay. Or you can use this more complex equation, which is pretty simple to put into Excel. and check things that way. Okay, so the last thing I want to talk about is there's a lot of great software available now to do anchor calc. So this is Simpson's, and they'll check headed studs, bolts, welded to the plate. They'll do a stress analysis on the plate, and then all of their anchors that they supply, you can choose those. So you can come in here and put the size of a base plate or an embed plate, the anchor spacing, the different loads. You can put moments on it and edge distances, and it does all the calculations we just looked at. And it's important to know how to use this software, but it's probably more important to know when it's running right and running wrong, so you have a way to know if it's something you should be trusting for your designs. Okay, so that's that for this. There's an anchorage example that I'll toss up and put that on Canvas for you. Then the quiz is also there ready to go. Anyway, we'll talk more in class. Thanks.